In this video, I'll talk about Ampere's law in magnetized media, and we have used really most often the integral form of Ampere's law, the closed path integral of B dot dl is equal to mu naught times I, the current enclosed. And I have emphasized the importance of the right hand rule when you decide on the integration, the direction of integration and the positive current. In differential form, we have the curl of B is equal to mu naught times the volume current density. Now, for our convenience, we distinguish between the free current density and the bound volume current density. The free is the one that we control, the bound is the one that is a result of magnetization of the volume of the material, and in particular it will be due to the inhomogeneous, to one that is a non-uniform magnetization. Now, moving on, the left side of this is the curl of B. Now I can do 1 over mu naught and I want to remind you that we have seen that we can find the volume bound current density as the curl of the magnetization, and since I have here the curl of B, I can move this term to the left side, and this will be the curl and this is equal to the free volume current density. Now, this quantity is what we call as H. This is the differential form of Ampere's law in magnetic media, and this is the curl of H is equal to the free volume current density. If you want to write this in the integral form, you'll have H dot dl is equal to the free current. In both cases, this is the enclosed, this is the enclosed current. Now, in a similar way that I emphasized in this integral form of Ampere's law, the same thing is true here. When you decide on the direction of integration, this is again a closed path integral, you have to be, that direction of integration needs to be consistent with the right hand rule and what you define as a positive free current. I do also want to mention the integral form of Ampere's law. This one is we saw that it was useful. It would give us, it can give us B, the magnetic field, if you have symmetry, of course, and if you know what is the current enclosed. In a similar way, this can, if you know the free current, and the reason why this is convenient, by the way, the reason why we do all of this is because what you control experimentally is the free volume current density. If you know what this is, then using this integral form of Ampere's law in media, you can find H, if you have symmetry, of course. So remember, the Ampere's law, in the same way as Gauss's law, is always valid. Okay, always valid does not mean that it's always useful.